Good day, I'm Dr. T and welcome to my office. So let's talk chemical reactions and go into a little bit more detail than I have earlier. So when we talked about chemical reactions last time, I talked about different types of chemical reactions, equations, etc. But let's actually zoom in a little bit. So for a chemical reaction to take place, you literally have to have the two reactants hit each other. Now, if it's a single reactant, that's a slightly different story. But it's kind of, a similar narrative, just, it's only with one player. So in order to have a chemical reaction, assuming you have two reactants, they have to literally hit each other. Now, when they do so, a couple of things have to take place. One, they have to hit each other in the right orientation. If they're going to make a bond between two atoms and that bond needs to be coming out at a specific angle, then they're going to have to hit in close to that angle where that new bond is going to be formed. If they don't, they simply bounce off. Now, how narrow that window of angles that they have to react is depends entirely on the chemical reaction. There's quite a few of them where it literally is any angle. It doesn't matter where they hit. Whereas others, you only have a couple of degree angle to actually hit. You've got a very narrow window to go for. As you can suspect, the reactions where you need a very precise collision in order for the reaction to take place typically are a little bit slower. You have lots of failed reactions, lots of reactions that collide, but they don't actually react. And so that's actually an area we want to jump into, and that's called kinetics. How fast does reaction rate take place? And of course, the window of collision, what angle you have to hit, is something that as chemists we have very little control over. However, there are other properties that are going to speed up or slow down a reaction that we can control. So if you think about a reaction, if you have to literally have two reactants collide with each other, then of course, what angle they collide in, but what's going to control whether or not they collide? Well, let's start with how many there are. The more reactants you have in a given area, concentration, then the more collisions you're going to get. If you think about driving in Orange County, California, versus driving in middle of nowhere, Wyoming, you're more likely to get into a head-on crash in Orange County because there's just more cars there. Middle of nowhere, Wyoming, good luck if you even see a car. And the same goes for the chemicals. The higher your concentration of your reactants, the faster your reaction rate's going to go. We can actually say that rate equals a constant, and then typically it's going to be multiplied by the concentrations of the reactants. Depending on exactly how the reaction goes, there can be coefficients there. And I'm not going to go into that. But you've got the concentration of reactants generally play a very important role in your chemical reaction. Some reactants more so than others, just depending on what your reaction is doing. The next one is going to end up being temperature. The reason why is that not only do the atoms, when they collide with each other, have to collide at the proper angle, which once again for some of them is any angle, others is a very narrow window, they also have to be going with sufficient velocity for them to rearrange the electrons that need to get rearranged. If they go and hit each other and they're moving too slowly, they just bounce off. Nothing happens. So they need to be going fast enough to achieve what's known as the activation energy. The energy needed to actually do the reaction for those two atoms. Now, the velocity of these things is determined by their temperature. The higher the temperature, the more individual atoms will be going quicker. So remember, this is an average, so there'll always be slow ones, there'll always be fast ones, but the higher the temperature, the more of them that will be going fast enough to create a chemical reaction. And therefore, more of your collisions will be successful. Now, once you collide, this is actually not done. It's not an instantaneous process. There is some time that takes place, a little bit of rearrangement. So during the collision, what you're going to end up seeing is the formation of a transition state. This is a very unstable configuration. These are electrons in flux, one where this setup is not sustainable. A bond will be broken, guaranteed. And so typically what you have is, a bond forming and a bond breaking or rearrangement of electrons, and they have to go to a different lower energy configuration. And that could be back to the way it was. And they could return simply back to the way it was. That happens. And therefore, hey, everything was right. It's just the reaction didn't take place. Alternatively, they go and they form the product. And thus, you have your reaction. Now, a couple of key parts of that transition state. One, you can actually get some interesting chemistry taking place in that transition state because sometimes there's more than one product they could form into. You know, you start breaking things, you know, they don't necessarily have to go to the certain direction. So this is where we sometimes get side products, things we didn't really want, but we got anyways. That's because transition state did a couple of weird things. Additionally, sometimes we run into what we call intermediates. These are similar to transition state, but they're a little bit different. These are typically molecules that are very, very reactive. Ones that are so reactive that as soon as they collide with anything else, they're going to react. But they are stable on their own. So these are something you could imagine, you know, floating around in space or something where there were no other reactions. And thus those can hang out. And so some reactions will actually take a couple of steps and will produce a couple of transition states and have a couple of intermediates going on inside of them. Now, one such set of reactions is that of the catalyst. So catalysts are a way of speeding up a reaction. What they will end up doing is fundamentally changing how the reaction works. Typically speaking, they're going to take a reaction that had one really unstable transition state, one where your two atoms just had to smash into each other ridiculously hard, and instead break that up into a bunch of transition states and intermediates, all of which don't take nearly as much force to do so. And that way, the average energy involved can be lower, and thus you can run your rate faster. Because you've lowered your activation energy by fundamentally changing the way the reaction works. A classic example is going to be the reaction of carbon-carbon double bonds with hydrogen in the presence of platinum. So instead of trying to cram those hydrogens on in one step, it will then take place over a series of steps where the carbons bond to the platinum, the hydrogen bonds to the platinum. One of the hydrogens will move over and join a carbon. The other hydrogen will then move over and join the carbon. And the platinum is returned to the way it was, which is the case always for catalysts. They always are returned to the way they were. And then, you know, now we have added those hydrogens onto that carbon. What used to be a carbon-carbon double bond is now a single bond with two extra hydrogens. So before I end this video, I should point out there's one more condition that controls reaction rate. And that is going to be when you have either a catalyst or a reactant that is typically either going to be a solid or a liquid. Solids and liquids aren't usually directly in the reaction mixture. Usually it's a solution or a gas where the reaction is actually taking place. Because of this, they can't react over the entire volume of the solid or the liquid. Instead, they can only react on the surface area. So, for both solids and liquids, the amount of surface area you have also controls reaction rate because it controls the number of atoms that can actually participate. Only the ones on the outside will be able to work. This is why if you take, say, some flour and pack it in real tight and try and put a light to it, you'll get a little bit of singed flour and nothing much. If you were to take some flour, though, by the way, flour, I mean literally the stuff you make bread with, and you fluff it up and you poof it up into a cloud and expose that to a flame, you can actually get explosion. There's been several cases of flour mills literally blowing up because of dust explosions. So do respect dust. It has very large surface area for its volume, and therefore it can react very, very quickly when you might not be expecting it to. So fine powders are always something you need to be concerned with. Just because, hey, reactions can take place really, really quick with those guys. So with that said, have a wonderful day, and I will see you in later videos.